Okay guys, I'm throwing in an extra video here to address the several questions that I've had coming my way about the pooling process in the two proportion z-test. So I'm going to try to knock out the questions about that as best I can with this extra video. So to start with, there is a 2-page reading that you could do that might be helpful for understanding the why behind we pool. It starts on page 548, 549, and it actually starts in this section, Will I Snore When I'm 64, to set up a scenario. And then there's an Everyone into the Pool section that talks about why we pool our proportions when we do a hypothesis test. So if you're looking for a little additional insight into that 2-page reading would take you maybe 5 minutes. It may be helpful to kind of condense it down into a single thought. When we do a confidence interval to compare two proportions, we're starting with the assumption that we're looking for differences between the two groups. So because we're addressing differences and we're assuming we're going to find differences in the two groups, we start with the assumption that the two groups are different, and therefore when we compute the standard error is really where the crazy stuff comes in. When we compute the standard error, this is your blue book, page 2. When you compute the standard error for two proportions, two populations that we're assuming are different, you use the standard deviation formula that we've been using all this time, which is this first one, the S for standard error of the difference of the two p hats is p hat 1 times q hat 1 over n1 plus p hat 2 q hat 2 over n2, and then take a square root. So that's the formula we've been using for a confidence interval, because we're assuming that p1 and p2 are different from the beginning. The difference with a hypothesis test is in a hypothesis test we start sort of at the opposite end. We start with the assumption that of innocence. There's nothing interesting going on. These two different populations are not different. They have the same proportion p. So on this next little section, starting right here, it says when p1 equals p2 is assumed. Well, that means this is done in a hypothesis test. This looks entirely different than the formula that was in the old books. And so you were looking at yesterday's video was a video that was based on the old formulas in the old formula books that they used to use on the exam up until this year. This year there's a brand new formula, which is actually more friendly than I expected it to be. So when p1 equals p2 is assumed, and that's the assumption we make in the null hypothesis, we're assuming the two proportions are equal, which is why we're assuming their difference is 0. And when that happens, you have this different formula. The structure looks more different than it really is, because we have this p hat c, which I'm assuming they mean p hat combined, the two groups combined instead of the word pooled, and 1 minus p hat c, which is q hat combined, multiplied by the sum of 1 over n1 and 1 over n2. If you compare it to the formula above it, the difference is you're using the same p hat q hat and then distributing it through to the first 1 over n1 and distributing it through to the second 1 over n1. So really, once you do distributive property, it's the same as this formula, except that p hat 1 and p hat 2 change to p hat combined and q hat combined. So it really is this formula rewritten for combined proportions. But on the day of the AP exam, this is the formula book you're going to have. So it just makes sense to take a look at using this formula. Then all you have to know is go look up that formula and substitute in some numbers. So that might be the most practical way for us to go from here. So I want to look at one of the homework problems, one of the Thursday homework problems I think would work just fine, and look at how to use this formula in the mechanics as opposed to the one that was in your notes that was in the old structure. What's in your textbook is what your notes look like. What was in the old formula books is what your notes look like. This is a new view on things that might help some of you that are having trouble dealing with the formula. So let's try this one. and see if you like it better. If you like it better, just use this one. And for heaven's sakes, on AP exam day, this is the one you're going to look up and use. But you got to pay attention to this when P1 equals P2. So you only use it when you assume they're the same, which means you only use it for hypothesis tests. Okay, so I'm going to move this out of the way to make some space. And we are going to flip to the homework set. And I'm just picking something not so randomly on the last problem of your homework for this chapter. Number 29 was a question about polling about voters about a candidate, and a before and after poll and how different they were. So if you haven't already looked at it, maybe we should just quickly read through the gist of it so that when we get into the mechanics, we're not just jumping into something in the middle and not know what we're doing. 1 month before the election, a poll of 630 randomly selected voters showed 54% planning to vote for a certain candidate. A week later, it became known that he had tweeted inappropriate pictures of himself, and the new poll showed 51% of 1,010 voters supporting him. So his approval rating has dropped 3% since the tweet. Do these results indicate a decrease in voter support for his candidacy? So part A is to test an appropriate hypothesis and state the conclusion. Okay, so I'm going to move the book out of the way so I have a place to write. And let's just go through the whole thing and put the new mechanics in as we go. So let's start with some assumptions. Find some blank space here. So the first thing we're going to assume is that the two percentages, the approval rating, are the same both before and after. Because in the null hypothesis, we're always going to assume that there's nothing interesting going on. There's no change, or the two groups, the before and after groups, are the same. Okay, so before we actually write our hypotheses, we're going to define parameters. We have two P's that we're examining. We have a proportion P before the tweet and the proportion P after the tweet. I like to pick subscripts that are practical for the context. So I'm going to let P sub B equal the percent voting for the candidate before the tweet, and then let P sub A be the percent voting for the candidate after the tweet. There's nothing wrong with using this sort of notation on AP exam. It communicates what's going on pretty nicely. So feel free to do that as long as you get your context clearly defined. Make sure that you are communicating that you're measuring a percentage of people voting. Okay? So null hypothesis should be that they're the same, that the tweet didn't matter. It didn't make a difference. So we're going to argue that the before and the after are equal. So we could say P sub B equals P sub A. I prefer to do a difference equal to 0 because then when I make my model in the mechanics, I have a number, a mean for my sampling distribution. So I'm going to, instead of saying P sub B equals P sub A, I'm going to say the difference of the two is equal to 0. If you have two of the same things, you subtract them, you should get a 0. If you write P sub B equals P sub A, full credit, it means the same thing. On the other hand, the difference, P sub B minus P sub A, on the contrary, we are arguing, well, we're looking for evidence that the tweet has made people less likely to vote for him. So we're looking for evidence that the before proportion would be bigger than the after proportion. So you could write P sub B is greater than P sub A, or you could write that the difference is greater than 0. If the before is bigger than the after, we should be getting a positive difference. Positive is greater than 0. I suggest you use subscripts that make sense in the context of the problem. If you use sub 1s and sub 2s, you have to work harder at keeping up with context, and that's more trouble than it's worth. Okay, then we check conditions. Okay, so it said in the problem that the voters were randomly selected. So voters were randomly selected for both polls. We have to check both the before and the after. You can do that in a single sentence if you're clever. Okay, you don't have to write two separate sentences, one for before and one for after, unless you're just a glutton for punishment. Okay, then we want to check independence within the groups, which could also be a sample size. So we could argue that in each before and after poll, each voter's stance is independent of other voters. We could also argue the 10% condition, and that is your override, and probably a little bit easier to write up. So let's argue the 10% condition. 630 and 1010 are each less than 10% of all potential voters. Do not fudge on this and not write a complete sentence. If you fudge and try to write something generic, something that's not in context, something that's not a complete sentence, there's a really good chance you're not going to get points for it on the AP exam. So those of you who are still trying to fudge and write 3 or 4 words, you're going to have to work harder than that on the AP exam. If you don't, you're wasting your time. So practice doing it right so that it becomes an automatic thing on AP exam day. Okay, and then we want to add a check. When we compare two groups, in order for the standard error formula to work, in order for that computation to be legitimate, it all boils down to random variable rules that we learned back in the probability unit. The two groups have to be independent of each other. So we're going to assume that voter opinions before the tweet are independent of those after the tweet. We need the two groups to be independent or the standard error formula does not work and our mechanics are wrong. So this is the extra condition that we weren't checking in the past because we weren't working with two groups. When you add two groups to the mix, you have to add a fourth condition. It's the only change. Last but not least, we have to check to make sure we have at least 10 successes and 10 failures in both groups. This is the longest part because you have to check 4 different sets of numbers. And you need to make sure you're labeling everything. So the number before times the p hat before is equal to 630 people times the 54% who said yes. If you round to the nearest whole number, that's 340, definitely bigger than 10. And we're using p hat and q hat because we do not have individual p's in the null hypothesis. We just know that we need them to be the same or different. We don't actually know values. We haven't proposed values for the true P and the true A. So we have to use the P hats and the Q hats for both groups because that's all we have. Alright, the number before times Q hat before is 630 people times the other 46%, which rounds to about 290 people. Those two numbers should still add up to 630 total. Okay, then we have in after times P hat after, which is 1,010 people and 51% said they were supporting the candidate. That's about 515 voters. Then in A times Q hat A, 1,010 people times the other 49% who are no longer supporting the candidate, 495 people approximately. And we see that all our successes and failures are at least 10. All those conditions seem to check. So a normal model can be used. Do a 2 proportion z-test. And now is when things get messier, because now is when we have to deal with the messy standard error formula. So mechanics are next. So I have the formula from the Blue Book written down here. So let's pull that out. Okay, so this is the formula we're going to use for standard error. It's the messiest part of the whole thing. But let's start with the big picture. We argue, because all of our conditions check, that the differences in voter approval, P hat B minus P hat A, are normally distributed because the conditions check. And in a perfect world where the null is true, that difference is 0. So that's that PB minus PA equals 0 from the null hypothesis. In a 2 proportion B test, that's always our argument. This center is always 0. Okay, we need to know where the actual observed difference is, and the observed difference is going to be found using a z-score formula. So let's do a z-score. I'm going to leave some space up here for some work. Z-score says take the observed difference in proportions. Okay, well, let's see. We had 54% before minus 51% after. So we're going to see a 3% difference in the two. This is always in the same order as we've defined our variables in the null hypothesis, so before minus after. So 3% difference minus the expected difference, which is 0. Now, I had a question yesterday asking me, do we really have to show the minus 0? Okay, mathematically, I know it doesn't make a difference. But in terms of communication, you are showing the reader who's giving you points that you understand that you're comparing the observed difference in proportions to the expected difference in proportions. And this minus 0 communicates that you know that that's what's going on. Write the minus 0 in there. And then in the denominator, we need a standard error formula, and that's where things get messy. So I have this standard error formula up here that I penciled in from the Blue Book because it was easier than pulling the Blue Book back out. I wouldn't normally write that on my paper. It's just up here for reference. So standard error is the square root of, so the denominator is standard error. You can compute it on the side and do extra work, or you can compute it right here. Okay? It's a little more efficient if you do it all in one step. Now I need a p hat combined first. Well, I've not computed that yet. I have to actually compute that separately. So I'm going to go up here and do p hat combined, or p hat pooled. We could write pooled there. But since this is the formula in the Blue Book, it's a little bit shorter. Let's just use it this way for this example. So x1 and x2 are the counts, your successes, from your two separate groups. So if I flip it back over, I'm going to remember that I had 340 successes in the first group and 515 successes in the second group. So 340 plus 515. So I've computed that back here. They are always whole numbers. You always round those to the nearest whole numbers. These are real numbers of people. Okay, so 340 plus 515, 340 plus 515 over N1 plus N2, so the sample size is combined. So 630 people in the first poll and 1010 in the second poll. So this is our p hat pooled or p hat combined. And when we add that up, when we actually add, and then divide, or just stick this whole thing in our calculator, it's going to give us approximately 0.521. And I have a calculator handy, but I'm not going to waste your time watching me type numbers in. You can do that all by yourself. So this is your p hat combined or p hat pooled. Okay, that's the number we're going to put here for p hat combined. Pull that down. So p hat combined 0.521 times 1 minus p hat combined. So 1 minus 0.521 is 0.479, so that's q hat. These two should add up to 100%. Alright, times in parentheses, 1 over sample size of the first group plus 1 over sample size of the second group. Alright, so this is a little less messy than the way the textbook does it, than the way it was in the original notes. You may like this better. But the real upside to this one is that this is the formula in the blue book, and it's going to be the easiest one to go to on exam day. Alright, and so you stick all this in the calculator just the way it looks. I'm going to actually, for those of you who are watching the video, being the good aspiring students that you are, I'm going to give you a bonus calculator lesson here today. Okay, so control divide, open parentheses 0.54 minus 0.51, or you could just put a 0.03 in there. Just watch your decimal places. Minus 0 doesn't matter. I'm not going to bother with that. Over square root of 0.521 times 0.479 times open parentheses, control divide, 1 over 630 plus control divide 1 over 1010. Oh, that's not a 10. Okay, so this looks just like the one on paper with the exception of the minus 0, which we know doesn't matter, and that's about 1.18. And I know I have a 1.17 in my copy of homework, and mine is because I didn't round off this number and this number. The 0.521 I had crunched out earlier and did not round it off. A 1-digit hundredth place decimal difference on the AP exam is not going to matter. It's a model anyway. It's not perfect. It's just the best we have to work with. Okay, and then we can do probability. Oh, well, let's make a mark first. So our z-score is 1.18, so a little more than 1 standard deviations above the mean is where our sample hits. So this correlates to a z-score of 1.18. And we want to know the probability of a difference greater than that, because our alternative hypothesis was that the difference was greater than 0. So we're going to shade in the greater than direction. So to finish it, we want the probability of a z-score bigger than 1.18, and that is menu, probability, distributions, normal CDF, lower bound of 1.18, upper bound of infinity, and that gives us a probability of what rounds to about 0.12, which is the same thing we get if we had the 1.17. Okay. So, with a p-value of 0.12, that is not a very unusual difference. It's just very little above the first standard deviation above the mean. That is not unusually high. So we are not going to reject. We don't have evidence against a difference of 0 that's substantial, that's significant. We will fail to reject the null hypothesis at an alpha level of 0.05. There is insufficient evidence of a decrease in voter support, which is the same wording we started with in the original problem. Okay, so the big difference here is this is a little less messy than what you saw in the notes. So I propose that we try the next time we work one to use this version that's in the Blue Book and to see if that's a little more manageable. Alright, so as a bonus for this morning, or afternoon, or midnight, whenever you guys are watching this, because you guys keep some really odd hours, I can tell from Schoology. Options for, oh my goodness, why is the glare, okay, the glare is really bad, guys, and I'm going to see if I can, oh, come on. Oh, there we go, maybe that'll be better. Okay, so a tool I've not shown you yet, because you've got to use it very, very carefully on AP exam, but it's usable. There is a menu that calculates p-values by doing hypothesis tests. You might have played around with it already, I don't know. If you go to menu and statistics, number 6, option 6 is confidence intervals. We already looked at that one. But what we haven't looked at together yet is stat tests, number 7. And you'll notice that there is a 2 proportion z-test. There's also a 1 proportion z-test that you could use to crunch numbers for a 1 proportion z-test. But understand, you have to show all the work in the mechanics. You can't go straight here, get a p-value, and just bank on that. The work I'm writing down here is minimum work on AP exam. You've got to write it all down to get all the points. But this can actually get you some number crunching done, maybe a little more efficiently. So number 6 is a 2 proportion z-test. Group 1, number of successes, rounded to the nearest whole number, was 340. If you put a decimal in there, it won't work. It'll say, I don't understand. This is supposed to be a whole number of people or things. You got to give me whole numbers. Except it won't really say that. It'll just say domain error, and you have to figure out for yourself what went wrong. 630 was their sample size. Make sure these are in the same order that you used in your null hypothesis. And then number of successes for group 2 is 515. And of course, these are numbers that you get in that last check of your conditions check. So you've already crunched those numbers by the time you get to this point. 1010 was the sample size. The alternative hypothesis, you have 3 options. When you drop down that menu, whoops, you can do a P1 is not equal to P2. That's a 2-tailed test. P1 is greater than P2, or P2 is less than, or P1 is less than P2. So we had a greater than in our null hypothesis. If you move your P2 to the other side of the equation, you could rewrite that as P1 minus P2 is greater than 0. So that first option is the one that we have in our alternative. So pick it and click on OK. And you get some really cool things. First of all, you get a z-score, 1.17. Hear me well. That does not replace showing how to set it up. If you do not show how to do this calculation, just writing down z equals 1.17 will not give you it won't get you point values for computing it. You have to show how to compute it. The p-value, 0.12. Okay, that agrees. So what you could find this useful for is to do the number crunching without having to type all the formula in on a calculator page. So that is maybe a bit more efficient. It does show us 54% for P1, 51% for P2. So of course we had rounded versions in our problem stem. These are the actual proportions they would have originally been. But the biggies are these top 2 pieces, because those can crunch the numbers for us in one step instead of us having to type all this in and then go back and run the normal CDF to get this. You can get it all in one fell swoop. So now that you know it's there, feel free to use it, but you have to show the work. You have to show the work. You have to show the work. There's no way around it on the AP exam. This will be a free response question, and you must show the mechanics. Okay, that's it for this one. I will wait for more questions and answer those as they come.